Okay, so from reading the textbook chapter, hopefully you notice that equivalent capacitance is very similar to equivalent resistance. It's just that they're backwards as far as series and parallel. So here's what I mean. I actually don't remember the rules by themselves for capacitance and how you find equivalent capacitance. I do, however, remember the rules for equivalent resistance. And I remember that the rules for equivalent capacitance are the opposite. That whatever the rule is for resistance in series, that's the rule for capacitance in parallel. So to find equivalent capacitance in a parallel circuit, CEQ is C1 plus C2 plus C3 and so on. And notice that is what would be the rule for resistance in a series circuit. And in parallel, for a capacitor, in series for a capacitor, it's what the rule would be for parallel in resistors. So in a capacitor, if you have capacitors in series, you do 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. So I just remember the rules for resistance and that the rules are swapped for capacitance. So in a series of capacitors, you add their inverses and flip it. And in a parallel set of capacitors, you just add them. It's the opposite of resistance. Let's take a second to think about why it is that it's opposite. The equation for capacitor is charge per voltage. And any given capacitor, so if I went to Radio Shack and bought a capacitor, and it has some capacitance C, that capacitor, no matter what circuit I stick it in, will always have that same capacitance. So its C is set by the materials in it, or by the shape of the plates, if you think back to C equals epsilon naught A over D. So the capacitance depends purely on just the capacitor, and that's for an individual capacitor. So if I could put that capacitor into a circuit, and let's start with parallel. If I put that capacitor into a circuit, this isn't parallel yet, it's going to have a given C. Now the amount of charge it can build up depends on the voltage of the battery. And in parallel, every capacitor would get the same voltage. You should remember that rule from dealing with resistors. Since each of these is independently connected to the battery, each one has its own path back, they each get the full voltage of the battery, which means they each get to store as much charge as if they were connected separately. And so, since each gets the same voltage, and each will gain the same amount of charge, every time you add one, you've just added up the amount of charge that whole thing can store. And so, by adding these in parallel, we can store more and more charge. And that's why when you put capacitors in parallel, the amount of capacitance simply adds up, because the amount of charge you are storing would simply add up. If we put them in a series circuit, however, remember any electron leaving the battery can only fall as far as the battery's initial V. And so that voltage does kind of get used up across each of the capacitors. And since each one gets only part of the voltage here, each one will get only part of the charge when thinking about that original Q over V, because the capacitance of each individual capacitor is set. And so each one will only get a little bit of the charge. And that's why we add their inverses, because each one's only getting a little bit of the charge, and we're decreasing that capacitance as we go along. Let's try a numeric example and then we'll be done. So let's say we have some battery with a certain voltage hooked up to the following set of capacitors. And here. Okay, so there's our circuit, poorly drawn as it is. And let's say this is a 10 microfarad capacitor up here, 10 microfarads. it's a mu, not an m, 5 microfarads on this one, and let's say 20 microfarads here. And I want to find the equivalent capacitance in that circuit. Well, just like in dealing with series and parallel circuits, I'm going to look for what's easiest and then go from there. These two here appear to be in series. So if I take the 10 and the 5 and I find their CEQ, I'm going to label that in red, so the CEQ of just the 10 and the 5. To do that, I would need to, since they're in series, 1 over CEQ, because remember it's the opposite of resistance. These are in series, so I'll do the inverses. 1 over CEQ equals 1 over 10 microfarads plus 1 over 5 microfarads. Looks like a clear common denominator of 10 there, so 1 over 10 microfarads plus 2 over 10 microfarads gives me 3 over 10 microfarads. And since that's equal to 1 over CEQ, CEQ is equal to 10 microfarads divided by 3, or about 3.33 microfarads. And the units here are nice enough that we can leave them in microfarads as we deal with them, not have to convert into typical notation and then back. Okay, so that's just for this part. So now I can imagine redrawing that circuit with a 3.33 microfarad capacitor still hooked to the 20 microfarad capacitor. And those are in parallel. So if I'm doing these two now, notice I just replaced those old two with the new imaginary one from the equivalent capacitance I just found. Now these are in parallel, so they just get added. CEQ equals 3.33 microfarads plus 20 microfarads for an equivalent capacitance of 23.33 whoops, that was sloppy, microfarads. And that's the equivalent capacitance of the whole thing. Works like resistance, except the rules are flipped. Alright, that's it. Make sure you read the textbook chapter, hopefully before watching this. And since this was such a short video, I've included a few extra practice problems for you to practice doing equivalent capacitance. That's all. Have a good night. See you tomorrow.